Atoms, molecules, and ions. All right, I'm not going to spend a whole lot of time. This may seem rushed, and it's probably because it is. I've got to get out of here at 1:45. I can't stay over. Normally, what I do is if I don't have any other obligations, I just stay over. And if that ever happens, and you have another class to go to, or you have other obligations, when the class is over, you can leave. And if I don't have obligations, I'll just keep talking and recording and post the video so you can see what you missed. And then there are always older videos like we talked about. We'll go back and look at it. I did have a technical problem with Tuesday's video. The voice and the picture weren't synchronized. So the first one I posted was out of sync, but I figured out how to, I had an audio file that was recorded separate. So I went back and put that one in there and shifted it to where it didn't look like I was making a foreign movie with dubbed in voices. So the one you see on there now should be synchronized pretty well. Okay, chemistry. Believe it or not, chemistry's been around for a very, very long time. We can go back actually even before the Greeks, but the Greeks were the first, ancient Greeks that is, were the first to make an attempt to explain why chemical changes occur. Now they were way off base, but at least they made the attempt. There were supposed to be 4 elemental forces that are involved in chemistry, right? Earth, wind, fire, and water. And they tried to take that and describe what was happening in those terms. There were a few ancient Greeks who actually believed in an atomic theory. In other words, everything was made of an elementary particle called the atom. The problem that they had was they thought that the atom was the same for everything. So you're made of the same atoms as that desk. So that they boxed themselves into a corner there also, because we know that's not the case. So they had to do some fancy gyrations to make that work. But that's how we got our start. Then we went through the Dark Ages, and I guess you would call them, I don't know what you call them, alchemists, were active through the Dark Ages, and they actually contributed some things to our understanding. In other words, they discovered several elements, and they also produced several mineral acids like sulfuric acid, hydrochloric acid, nitric acid, and they were produced for their practical effects. They were able to dissolve things, and that was, well, some of them, I can't say that all of them had this ambition, but a lot of them did. They were looking for the elixir of life. Even Isaac Newton was an alchemist. And then there are a few of them that wanted to transmute elements, right? Turn lead into gold and that type of thing. But they made contributions, and those contributions worked their way into what we call modern chemistry. Robert Boyle, who was an English scientist, back then they called them natural philosophers, is considered to be the first chemist. And he published The Skeptical Chemist in 1661. So we're getting started in the 17th century. We're starting to ease our way into modern chemistry. And probably because he was given that designation because he was involved, his investigations were quantitative. In other words, he weighed things, he measured things that were part of his experiments. And he also proposed a definition for the element. Now, when the concept of the element was accepted, there were they had to have a way of representing the elements. And this is one way. So you see all those symbols, right? That's a far cry from the symbols we use for the elements now. And it's a good thing that these guys did not win out, because I don't know about you, but that would have been a nightmare to try to do chemistry with those symbols. We'll talk about how these symbols came about in just a few minutes. All right, so the first thing, this is the way historically chemistry and actually other sciences were actually an accumulation of observations that led to proposed laws. This is how things behave. Under these conditions, you always get these results. And no attempt, well, attempts were made at explaining why, but they weren't very successful yet. So the laws are the ones that actually had teeth, had claws, and gained acceptance over time. First one of those was proposed by a Frenchman, Antoine Lavoisier. His was the law of conservation of mass. So in a chemical reaction, he said that the mass of the reactants that go into the process will equal the same mass as the products that come out of the chemical reaction. Unfortunately, Lavoisier was active during the French Revolution, and he had bought a contract from the king to collect taxes, which was perfectly normal back then. If you paid the king a certain amount of money, you could get a contract for this area, this population, and you collect taxes, pay the king taxes, what he requested, and everything else you got to keep for yourself. That's just the way taxes were collected throughout history. But when the French Revolution came along, the masses didn't agree with that, right? And those in power decided that he didn't deserve to live. So he lost his head with this brand new invention called the guillotine. And that cut his career short. Then I think this was another Frenchman, Proust, came up with the law of definite proportions. And all this says is that when you identify a compound, a pure substance, a compound, which was known to be a combination of two or more elements, right, that it didn't matter where the compound came from, whether it was purified from some natural source like an ore of some kind, or whether you produced it in the laboratory from a chemical reaction. Those two compounds had exactly the same ratio by mass of the elements that were contained in them. So it didn't matter the source. The identified compound had the same composition no matter what the source was. This is the law of definite proportions. And these laws are still valid today. Dalton came along. John Dalton was an Englishman, and he proposed that a series, we call them a homologous series because they're made of the same two elements. So, and I use the example of nitrogen and oxygen. For instance, you have nitrogen combined with oxygen, and these are different compounds, but they're made of the same two elements. And what Dalton proposed, and he didn't know this at the time, right? He didn't know those ratios that way. Everything was done by mass of one element, ratio to a mass of another element. If you give the mass of one element a unitary value, whatever it happens to be, that would equal to 1, say 10 grams or 20 grams is 1. Then the second element is proportion among the three or more different compounds in whole number multiples. That is, if we have 10 grams and 10 grams, and this will be 10 and 20, and this will be 10 and 30. That's the law of multiple proportions. Now, later on, Dalton is going to propose why that is. And he's going to be accurate. He's successful in proposing that. This is why that law is. In fact, he combines several of the laws into his atomic theory and explains why all these laws work. We'll get to that in a few minutes. Back a few seconds. So Dalton's atomic theory was proposed in the early 19th century. And he said that all elements, each element is made up of tiny particles called atoms. The elementary particle is an atom. That is the smallest division of the element that retains the properties of the element is an atom. And he borrowed this concept from the Greeks, right? I mentioned last time, I think, atome means not cut. It's the smallest particle. And he said, so each element is made up of tiny particles called atoms. And here's where he corrected the Greeks' mistake. He said, all atoms of a given element are identical, but atoms of different elements are different in some fundamental way. Now, he didn't know why they were different. He just knew that they were different. And that's part of his proposition. We know now why they're different, because their subatomic particles are different. And we'll talk about that also very shortly. He said that chemical compounds are formed by associations of these atoms. Right? So if we get an atom of nitrogen and an atom of oxygen together, you get nitrogen monoxide. If you have nitrogen and two atoms of oxygen, you get nitrogen dioxide and nitrogen trioxide. So that was the third postulate of Dalton's atomic theory. He's explaining why these things happen. And that's why the multiple proportions work. Because if you have two atoms, you're going to have twice as many in the ratio. Or if you have three, you're going to have 3 times as much mass in the ratio. He said also that chemical reactions are simply rearrangements of the atoms. They just swap dance partners. Right? And that's why Lavoisier's law of conservation of mass works. Because if you just switch them around, you still got the same mass before and after. They just change partners. All right. Okay. Now, after that, we have another Frenchman, I think, Gay-Lussac, who measured the volumes of gases before the reaction and after the reaction. And he combined his work with that of an Italian scientist, Avogadro. Gay-Lussac, his work was important, but Avogadro's hypothesis that came out of this type of investigation is the more significant. Avogadro says, and this is the best way to approach it, scientists at that time were working with gases because they were easy to deal with. And in the physical terms, the physical laws, the gas laws, and we'll get to those in chapter 5, gases behave physically the same, no matter what the gas is. And that's because the particles are so far apart, they don't interact. It's as if it's all empty space anyway. So the particles, the gases, that the molecules or the atoms that are in there really don't matter that much in physical terms. And that permitted scientists to work with these gases as if they were all the same. Avogadro came along and said that if you have any gas in a confined space in this volume, and you have another gas over here, a different gas, and they have the same volume, right? Volume 1 equals volume 2. And they're at the same temperature, right? And they're at the same pressure. If all those three are exactly the same, then the number of particles or molecules or atoms, whatever the case may be, number of particles contained in each one is equal. And that's my symbol for moles. We talked about moles as a counting number, right? The number of particles in this one equals the number of particles in this one if all of them are equal. Okay. The significance of that hypothesis is that if you have a gas that, say, this one's composed of hydrogen and this one's composed of carbon dioxide, they have the same number of particles. How about their mass? Masses will be different. This will have less mass than this one. And that's how we associate the mass of the individual atoms or the individual molecules with one another, because now we know that they're exactly the same number of particles, but with different masses. How do they get there? They get there because that individual particle weighs less than that individual particle. So that's how we get at the atomic masses and the molecular masses. That'll come later. All right, this is some of Gay-Lussac's work. He noticed that 2 volumes of hydrogen, and this all occurs at the same temperature, the same pressure, and temperature, pressure, and volume. Well, the different volumes, actually, in this case. 2 volumes of hydrogen and 1 volume of oxygen only gives 2 volumes of water. So in chemistry, 2 plus 1 equals 2 in this case. Sometimes 1 plus 1 equals 2, and sometimes 3 plus 5 equals 4 in terms of volume. Okay. Here's a case where 1 plus 1 does equal 2. And here's why 2 plus 1 equals 2. If we have 2 volumes of hydrogen, that means we have twice as many particles as in the oxygen container, because there's only 1 molecule each. But in hydrogen, 2 volumes means twice as many particles. So we have twice as many hydrogen molecules plus a unit of oxygen molecules. Put them together, you get, the outcome is 2 volumes of water, because you're making 2 particles of oxygen out of 2 hydrogens and 1 oxygen. Right, that's the explanation for Gay-Lussac's results. Now, when you put 1 volume of hydrogen, that means there's only 1 hydrogen molecule and 1 chlorine molecule. Remember, these are diatomics. Remember the diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomics at 1 atmosphere pressure and room temperature. So if you have 1 volume of hydrogen, you got the ratio of 1 hydrogen molecule to 1 chlorine molecule makes 2 hydrogen chloride molecules. So 1 plus 1 does equal 2 in this case. All right. Now we're going to find out what atoms are made of. We're getting to the point now, as time passes, okay, we're into the late 19th, early 20th century. An English scientist named J.J. Thomson was interested in negative, positive charges, right? Electricity was all the rage in Europe through the late 18th through the 19th century, right? It was a parlor toy, right? Bring it to parties. You could produce an electric charge by rotating this glass cylinder and touching it with what was it? like a rabbit's fur. You could build up charge on that thing. And then what you would do is you'd line everybody up and they'd all hold hands, and then the one on the end would touch the charge and they'd all jump, right? And have a big old time and drink some more wine. But some of the scientists were interested in what those charges were actually made of. And there was one device called a cathode ray tube that was being used by scientists to investigate these charged particles. J.J. Thomson noticed that this cathode ray tube, and it didn't matter what the material was at one electrode, would produce a beam of particles that behaved exactly the same way every time you treated it. Either with an electric field or a magnetic field, it would bend a predictable way each time. So we deduced, based upon how the beam bent, that it was composed of negative charges, all negative charges. And in fact, he worked out the ratio of the mass of these charges to their charge value. That's as far as he could go. He didn't know how much mass each one had, but he knew what the ratio of the mass to the charge was. And when he discovered that these electrons, the source of the electron was coming from an atom, right? And everybody knew about Dalton's work by this time, that if these were coming from the atom, then they knew that the atoms were neutral, right? So the rest of the atom must be positive to neutralize the charge, right? He didn't know what caused the positive charge. He just knew that these particles, these electrons, were coming from atoms. So what was left over had to be positive. And this is a cathode ray tube. I've got some videos embedded in here, but I don't think I have time to show them. I'll include them in the recorded version if you want to go look at them. But this was the cathode ray tube, a reconstruction of the cathode ray tube that they were using at the time.
Cathode rays are produced in a discharge tube. A vacuum pump is used to evacuate the discharge tube. The cathode of the tube is connected to the negative terminal of the battery, and the anode of the tube is connected to the positive terminal of the battery. It was observed that, at normal pressure, the gas did not allow the current to pass through it. However, when the pressure of the tube was reduced to 0.001 mm Hg, and a high potential difference between 10 kV and 20 kV was applied, at the end of the tube, a glow was seen on the walls of glass tube. The rays emitted by the cathode travel towards anode. The attraction of rays towards anode reveals that the rays carry negative charge. Properties of cathode rays are: 1. When any object is placed in the path of the cathode rays, these rays cast shadows. This shows that cathode rays travel in straight line. 2. When a wheel was placed in the path of cathode rays, the wheel rotates. This shows that rays consist of some particle and some kinetic energy. 3. In the presence of an electric field, the rays are deflected towards the positive plate. This confirms that cathode rays consist of negatively charged particles. 4. In the presence of a magnetic field, the rays are deflected. This shows that the cathode rays are affected by the magnetic field.
Okay, so we've discovered the electron, and now science research in this area was starting to cross the ocean. Right? American scientists were getting involved, and they were making progress. Robert Millikan was a college professor who was active in this area, and he wanted to know what was the value of the fundamental charge of a single electron. J.J. Thomson had given them the ratio of the charge to mass, but we didn't know what the fundamental charge was. And if you knew what the fundamental charge was, and you took Thomson's value, then it was a simple calculation to tell you the mass of an electron. So once Millikan had determined that the charge on a single electron was 1.6 times 10 to the minus 19th coulombs, and coulomb was a unit of charge in those days, right? Then he used J.J. Thomson's value and determined that the mass of an electron was 9 times 10 to the minus 31 kilograms. So it was very light, very small particle. He got a Nobel Prize in physics for his work. Actually, his Nobel Prize didn't come from his work on the electron. It came from his work on the photoelectric effect. Einstein got, I think it was 1921, Einstein got his first Nobel Prize when he mathematically described the photoelectric effect. And we'll talk about that later. And then Millikan came along and showed it in the laboratory. So Einstein was theoretical, Millikan was practical, proving that Einstein was correct anyway. Maybe I'll let you see the next video. That it would be descriptive. What you're going to see is an artist's rendition of Millikan's experiment called the oil drop experiment. Is how he determined the value of the fundamental charge on an electron.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
There, that's it. Okay, so Millikan and his graduate students performed this experiment thousands of times so that they could weed out the outliers, those values that just were experimental error. And that's why he could determine the value so accurately. Okay, now we've got the atoms are made up of electrons. Let me see. Let me look at my hard copy so I won't steal my own thunder. It's not in there, but I'll mention this. So we're starting to develop an idea that atoms are not just jelly sacks, you know. They're actually made of subatomic particles. And at this point, all we knew was that there were electrons in there, right? Electrons in the atom. So that means we had to have equal positive charge in there somehow to balance that. Well, the first model that was devised was called the plum pudding model. And if anybody's ever had a plum pudding, you know, it's got a matrix and then there are pieces of plum embedded in it. Those were the electrons, the pieces of plum. And the rest, the matrix was just a diffuse positive charge, enough to balance the negative. That's the plum pudding model. We're going to shoot holes in that in just a few minutes. But we needed an understanding of radioactivity, right? At this time, around this time, there was a lot of work being done by some scientists, Henry Becquerel and the Curies, Marie Curie, for instance, working with radioactivity. And what had been identified was that there were fundamentally three types of radiation that were being emitted by atoms as they decayed, as they changed from one element to another. So transmutation was identified, and the products were radiation. Well, the gamma radiation was light, just high energy photons. Beta radiation was actually electrons that were coming from the nucleus, and they were traveling at very, very high velocities. And then the other was alpha radiation, which was the helium nucleus. Right, so we'll learn how to do this in a minute. So we had 2 there and 4 here, and with a 2+ charge. So the helium nucleus was responsible for the alpha particles. That means they were huge by comparison to the beta particles, for instance. And that's going to be significant here in a few minutes. So Ernest Rutherford was an English scientist who was interested in how the atom was constructed. And he said, this just does not make sense because we got electrons as particles. Why don't we have the positive charge as particles too? And his proposition was the nuclear atom. He proposed, right, this is his hypothesis, that the atom is made up of a nucleus, and we knew that the electron was very light. So it did not account for all the mass. Almost none of the mass was in the electrons. So he said the rest of the mass had to be in a central location. And he said that's where the positive charges are located. And then the electrons were out here somewhere in this space. So the size of the atom was mostly empty space with electrons in it. So in order to prove his hypothesis, he devised this experiment we call the gold foil experiment. So he knew that he needed some way to probe atoms. And he also knew that gold foil could be hammered very thin without losing its integrity. Right? Like the Capitol in Charleston is coated in gold foil. That was what, 10 years ago or maybe 15 years ago. They recovered the Capitol dome in gold foil. So just a few ounces of gold was enough to coat the whole dome because they hammered it so thin. And it's just a few atoms thick. He knew that if it was more than a few atoms thick, then when he fired these alpha particles at his target, it would just stop it. Right? There'd be too much mass in the way. But if it was very thin and he only had 3 or 4 atoms thick, then he could probe that and see what happened on the other side. So he fired these alpha particles at gold foil, and he had detectors, probably photographic plates, all around. So when they struck this gold, then they could do one of two things. If the plum pudding model were accurate and the mass was not concentrated anywhere, and it was neutral all the way through, then these particles would go straight through and produce a bright spot right there, and that's it, nothing else. But if his model was true, most of the alpha particles would be detected on this side in a spot, but some of them might get close enough to the nucleus, right, which is positively charged, to be deflected, right? Positive by two means: either positives repel positives, or they just simply struck it and the mass deflected them. But they would end up over here, and some back here, and some back there, like that. So he ran his experiment, and guess which one came out? This one. So the nuclear model of the atom was correct, and the plum pudding model was defunct. This one doesn't have any narration with it, but it does illustrate the apparatus that Rutherford used. Okay, so we've got our gold foil set up there with the detectors. And those two plates sitting out in front of that green object are collimators. It simply means that when the particles are traveling, they might go this way, this way, this way. The only ones that are going to get through in a straight line are the ones that are perfectly aligned with these two slits. That's called collimation. Your beam is collimated, it's straightened. And that's what was observed. Okay, so now we know that the nuclear model is the correct model for the atom. And most of the density, most of the mass of each atom is contained in the nucleus with the positive charge there. And the electrons are out there in the rest of that space. Right? Okay, so now, at this point, we know that atoms are composed of protons, which carry the mass, most of the mass, and the positive charge, and electrons that carry the negative charge. But Rutherford did a few calculations and determined that the protons do not account for all the mass of the atom, right? A lot of the mass, but not all of it. He said there has to be something else in there that's very massive, but since we have enough protons to neutralize the electrons, whatever's left over has to be neutral. And that was called the neutron. So he set his graduate student, by this time I think he was a research assistant. Anyway, his name was Chadwick, James Chadwick. And he set him the task of finding out what was responsible for the rest of that mass. And he determined with his experimentation that these were neutrons. They were neutral. They were about the same mass as a proton. And he got a Nobel Prize for it. So now we know that the atom is made up of these subatomic particles: protons, electrons, and neutrons. What we got to do now is figure out what's the significance of each one. All right, well, the nucleus is very small compared to the whole atom, right? And that creates another problem. I mean, what are the limits of the atom? They have to be the electrons because they're out here. but it depends on their environment as to whether they're kind of squished or they spread out. So the dimensions of an atom are variable depending on its environment. Okay. So now I'm going to go ahead and we've got a slide on this, but I'm going to do it now. Stream of consciousness. Say this is our symbol for the atom or the element. Okay. There are 4 positions around that symbol that are reserved for information. Okay. This position up here is for charge. If there's nothing there, you can assume it's neutral. Or you can put a 0 up there if you want. It doesn't matter. Over here is the number of atoms. So if we have oxygen gas O2, that means 2 oxygen atoms are connected to make that molecule. Over here, we have number of protons, which is equal to, we give it the variable Z, which is the atomic number. Number of protons. And up here, which is, we give it the symbol A, is equal to the mass number. The mass number is always a whole number. It's the sum of the protons plus the neutrons. Right? So if you want to know how many neutrons are in that atom, you take this number and subtract that number. And you got the number of neutrons. So why do we need to know how many neutrons are there? Because of isotopes. The identity of an element, or the atoms within an element, is fixed based upon the number of protons. The atomic number is unique for each element. If you change the number of protons, you got a different element. Okay, so hydrogen has 1, neon has 10, iodine has 53 protons in its nucleus. That's the atomic number. It's always the same for each element. So they're joined at the hip. I means 53. Okay. But the mass number, being a combination of number of protons and the number of neutrons, can change. That mass number might be different for one isotope of the element versus another isotope. Carbon's a good example. So if we have carbon 12, that has 6 neutrons. Or if we have carbon 13, that has 7 neutrons. Or if we have the radioactive carbon 14, that has 8 neutrons. Okay. Now, the isotopes have virtually identical chemical properties because the chemical properties are determined by fundamentally the protons, but the chemistry of the atom is determined by its electrons, right? How do we know about the chemical behavior of an element? How it behaves, how it reacts with other elements, right? That's the chemical nature. So how do they interact? Well, now we know with the nuclear atom that when they approach one another, what do they see first? Electrons. So the electrons determine the chemical nature. And if it's a neutral atom, the number of electrons equals the number of protons. So for this one, and this one, if they're all neutral, right? We had a 0 here, here, and here, they would all have 6 electrons to balance the protons. Okay. If we made an ion out of them, let's see, say we had, well, let's use something different. Say we had sodium. Sodium has 11 protons. Okay. And let's say it's a mixture of isotopes. We don't care about what the isotopes are. We just worry about chemical behavior. So with 11 electrons and 11 protons, we have a neutral atom. But say we let it react with something like chlorine, which is 17. Okay, it has 17 electrons. Well, the nature of sodium as a metal is it wants to give up electrons. In fact, it only wants to give up one. So if it gives up one electron, it has 10 electrons left. That means overall it has 11 positives and 10 negatives, which means it's an excess one positive, right? Where does that electron go? Say that electron goes over here, because nonmetals love electrons. So now we have, instead of 17, we have 18 electrons. So now what's the balance? One negative. I took that negative from here, make this one a positive, took that one over there, made this one a little excess by one. So now this one has a negative charge and that one has a positive charge. I'm getting a little ahead of myself, but it seems to fit. Most elements, I should say all elements, in nature are a mixture of isotopes. So for our purposes, we don't want to, as chemists, have to deal with knowing about isotopes and what isotope we're dealing with in a chemical reaction, because they all behave similarly. What we do want to know is what is the contribution of each isotope to the overall. Right? So we don't have to deal with it, right? We don't need to know that we're working with carbon 13 or carbon 12 or carbon 14 in our reaction. We just want to know carbon. So what we want to know is what's the naturally occurring ratio of each one. What percent is this one, percent is that one, and this one doesn't matter because it's radioactive anyway. It's going to be around for a little while and then it's gone. So we want to know a weighted average of the mass, which means it won't be a whole number, right? It's kind of like your grade point average. Right? Your grade point average is not a whole number unless you got a straight 4.0. Right? But usually it'll be a fraction of some kind. Hopefully like 3.5, that'd be good, 3.6. Don't want to drop below 3, right? Especially if you're in a selected mint program. Right? They don't like anything less than 3. So there's our sodium. These are two isotopes of sodium. Right? Has the same number of protons, different number of neutrons. And we already talked about this. Right? That's the slide on my, these positions are reserved for that information. Now, when we go into the, when we're representing symbols for our atoms, our elements, for chemical purposes, we don't have to put this in here. It's only when we're talking about the subatomic nature, right? If we've got the symbol, we know it's easy to find out how many protons there are. Just look up there. What we want to know for chemical purposes is there a charge and how many of them are there? That's where chemists work. Okay, so if we have X has 23 protons, and it's 28 neutrons, right? What's the mass number? 51, right? Okay. What element is it? 23 protons. We'll go over here, right? From top to bottom, left to right, things get bigger. So we look for 23. We just keep following along till we get 23. That's vanadium. So our element is vanadium with a mass of 51. Okay. All right, let's talk about bonding. We've got the laws and the atomic theory from Dalton. Now, how's that going to affect our bonding? Well, when we form a compound, we have essentially two types of bonding, right? I'll say this. Nature just does what it does, and we're trying to make sense of it. And one way that we can make sense of how compounds are formed is to split them into either covalent bonds, right, where electrons are shared, or ionic bonds, where there's a complete transfer of electrons, like sodium chloride. But as a matter of fact, in nature, it doesn't think that way. It doesn't think in terms of only sharing or only ionic. It's like on a continuum. It just does what it does. And this is how we're trying to make sense of it, right? So don't make the mistake of thinking that nature believes all this stuff that we're telling it. This is just how we're making sense of the natural world. With the covalent bond, when two or more atoms come together and no one has a strong enough attraction to remove an electron from the other one, then they compromise. They share electrons to form a bond. That's a covalent bond. And when covalent bonds are formed, you get a molecule. That is a new unit that behaves as a single. So when we have hydrogen coming together with oxygen to make water molecules, those water molecules behave independently. Okay. Whereas with ionic bonds, we form ions, sodium ions and chloride ions, for example. Now, the thing that holds them together is electrostatic attraction. Positives attract negatives. And you don't get molecules there. You get an accumulation, an array of positives and negatives. So if we're using sodium ions and chloride ions as an example, you'll have chloride surrounded, sodium surrounded by chloride ions, and in 3 dimensions, right? You'll have one behind and one in front. And then you'll have a sodium over here, like that, and it just go on and on and on forever. So we don't have single molecules. These don't behave as a single unit like that. Right? It's a crystal array of positives and negatives. So I've got a video coming up that I'm not going to have time to show you, but I'll talk about it when we get to it. Terminology, right? We talked about ions so far. Ions are just those atoms that have an unbalanced charge by either adding electrons or subtracting electrons. What would happen if we did it with the positive charges? Add positives or subtract positives? You change the element, right? If you wanted to make an ion out of removing or adding protons, you change the element. So we only make ions by adding or subtracting electrons. Okay, all right. The positive ions are called cations because they've lost electrons and now they have an imbalance toward the positive. Anions are negative ions because they have an imbalance toward the negatives by gaining electrons. Just memorize that.
So this is a video that addresses the question that students often have: what is the difference between a formula unit and a molecular formula? And that brings up a couple of questions itself. What are the structural differences between ionic and molecular compounds? And how do those differences affect their chemical formulas? So the chemical formula for a covalent compound is a molecular formula. And the chemical formula for an ionic compound is called a formula unit. So an example of a molecular formula, H2O, which is water, and for a formula unit, NaCl, the formula unit of common table salt. So what's the diff? And if we look at the structure visually, I think we can see very much what the difference is. So let's first look at sodium chloride. This will be our example ionic compound. NaCl does not exist as a single unit. like a molecule. And this goes for all ionic compounds. So this would not be a valid way to represent sodium chloride. And like any ionic compound, in the solid state, sodium chloride exists as a crystal. So a very, 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 very tiny crystal would look like this with alternating sodium and chloride. And a little bit of a different view. The formula unit is NaCl, but if we look inside the crystal, the sodium and chloride ions are actually bonded to 6 oppositely charged neighbors. So if we shrink the ions, we can take a better look inside. And it's a little bit hard to see. So what we're going to do is take a look at a particular chloride ion, that one right there, and ask the question, how many sodium ions is the chloride ion close enough to bond with? Let's start with the head-on view first. And as we change the perspective, you can see there are exactly 6 sodium ions that the chloride ions is equidistant and can bond to. If we ask the same question of sodium, how many chloride ions can it bond to? Well, again, there are 6 chloride ions that it's equidistant to, and therefore the sodium ion also bonds to 6 chloride ions. So as you go throughout the crystal, you can see that is always the case. Because each sodium is bonded to more than one chloride ion and each chloride ion is bonded to more than one sodium ion, then you can think of all the ions in the whole crystal part of one single bonded unit. And the crystal below would be Na32Cl32. So you can imagine that would be very impractical given the enormous numbers of ions in a crystal large enough to see with our eyes. So only the ratio of ions is given, and that would be its empirical formula. But we call the empirical formula of an ionic compound the formula unit. And sodium chloride is the formula unit for the sodium chloride crystal, and it is the smallest whole number ratio of sodium and chloride ions in the crystal. So all formula units are the smallest whole number ratio of the ions in the crystal. That goes for all formula units. Here's another example, calcium fluoride. You've got 1 calcium for every 2 fluorides. The calcium is 2+, the fluoride is 1-. It has a slightly different crystal structure to account for, rather than the 1-to-1 ratio of sodium chloride, you have a 1-to-2 ratio of calcium fluoride. And if we shrink the atoms to take a better look and see how the calcium is connected to the fluorides, you can see that each calcium has 8 nearest fluoride neighbors, and so it is equally bonded to those 8 fluoride neighbors. And if we look at the fluorine, each fluoride has 4 closest calcium neighbors. And again, like sodium chloride, the whole crystal acts as one single bonded unit, and so we need to express the formula as the lowest whole number ratio, being CaF2. So what about molecules? How are they different? Let's take a look at water. We've got the space-filling model on the left, ball and stick model on the right. It's covalently bonded hydrogen and oxygen. And a collection of water molecules is just that, a collection of individual units of H2O that are covalently bonded single units of 2 hydrogens and 1 oxygen. They're not connected to each other except by weak forces. And so large amounts of H2O, any attraction between the water molecules due to weak forces, the molecules they still behave as individual units, not one large bonded unit as in an ionic crystal. Another view of water, here the hydrogens are white instead of yellow. And this I'm showing you to contrast more specifically with the sodium chloride or the calcium fluoride, because we showed the ionic crystals as solids, and here's water as a solid, ice of course. And here, like ionic compounds, molecular compounds also form crystals in the solid state, a very ordered structure that you can see here. If we take a closer look, however, we can see that each H2O remains as a single unit and is not covalently bonded to any other H2O. The attractions that hold them in place are, of course, the very, very strong dipole, the hydrogen bonding that occurs between the hydrogen and the oxygen. But that is much, much, much weaker than the covalent bond between the hydrogen and the oxygen, and the H2O therefore remains a single unit. So we look at these structural differences between molecules and ionic compounds by how we express them in their formulas. The molecule is represented by a molecular formula showing all the atoms present in the unit. The ionic compound is represented by the ratio of its ions, and that is called a formula unit. So here's the H2O molecule, and here versus the NaCl formula unit. Many sodiums and many chlorides, yet it's still just expressed as the lowest whole number ratio. It's 1 sodium to 1 chloride. In summary, in a molecule, the atoms given by the formula are all covalently bonded. In a collection of those molecules are attracted to each other by weak forces, but no covalent bonds occur between the molecules. The molecules exist as individual units of covalently bonded atoms. But in an ionic compound where the bond is the electrostatic attraction between oppositely charged ions, each ion is bonded to each of its oppositely charged neighbors. So for any ionic compound, all the ions in the whole crystal can be thought of as part of one single bonded unit. So the formula unit shows the lowest whole number ratio of the ions rather than representing very awkwardly all the ions in the crystal, which in most cases would be impossible to determine anyway. So that is the difference between a formula unit and a molecular formula.
So if we have this X plus ion, okay, with 54 electrons and 78 neutrons, 78 neutrons and 54 electrons. Okay, we want to know what's the mass number. Well, if it's one positive charge, how many protons do we have? We have one more proton than electrons, correct? So we have 55 protons. And 55 plus 78 is 143, correct? Did I lose anybody? Oh, excuse me, 33. Can't even add. 133. There we go. That, did everybody see where I got that? Okay. By the way, it doesn't ask you, but what's the element? 55? That would be cesium. Right? 55 protons. Okay. So which of the following statements regarding Dalton's atomic theory are still believed to be true? Elements are made of tiny particles called atoms. Yep. All atoms are given of a given element are identical. Nope. Because of isotopes. Right? They're not true anymore. A given compound always has the same relative number of types of atoms. Oh yeah, that's still true. Atoms are indestructible. In chemical reactions, yes, that's true. But they're not indestructible if you fire neutrons at them. Right. So those two are still true. Roman numeral 2 and 4, those are modifiable. Okay, let's talk about periodic table. The way it's organized. This is going to be your best friend. Periodic table can be set up. It can be like this, that. Let's see. We'll come over here a little bit, and then we'll come over here a little bit, down like that. That. And then we've got hydrogen up here and helium. The table is divided into sections, gross sections in the beginning, right? Metals versus non-metals. You're going to see, it's hard to see here, but there's a dark red line that starts here and goes zigzag like that. Once you get it started right, then you can follow it zigzag all the way down, stair step. If you start it in the wrong place, say you started here, you start here and go too far, then you're going to get it wrong. So that zigzag says that this side, let's see, kind of like that, These are nonmetals. These are metals. So most of the periodic table is metals. Now they have common characteristics. Metals are, to all but one at room temperature is solid. Right? The only one that's a liquid at room temperature is mercury. Now gallium's pretty close. It has a very low melting point. If you put a solid piece of gallium in your hand, it'll melt. But at room temperature, mercury is the only one. Whereas nonmetals can be any of the three phases. They can be solid, liquid, or gas. Now, if they're solid, solids over here are going to be malleable. They're going to be ductile. You can stretch them without breaking. If you polish them, they'll be shiny. Over here, if they're solid, they're going to be brittle. And not shiny, very dull. Now, we have other subdivisions, right? And if you work out that extra credit for the periodic table, you'll learn some of these. There are groups or families. Those are the verticals. And they have similar characteristics. They're not identical, but they're similar, right? The noble gases, they don't play with anybody. They don't make compounds unless you force them, right? Some of the heavier ones you can force into compounds. But typically they don't. They're just individual atoms. Next one over, right? Fluorine, chlorine, bromine, iodine. Those are the halogens. They have similar behavior, chemical behavior. Then the next ones are the oxygen group, right? Oxygen group, the chalcogens. That's an ancient term. The oxygen group, they have similar behaviors. And then the pnictogens, starts with a P, but the P is silent. The nitrogen group, right? They have similar characteristics. Then carbon group doesn't have a name. Boron group doesn't have a name. Go over to the far left-hand side. The first one in the far left are the alkali metals. They have similar behaviors. We're eventually going to find out why that is. And then the next group over for the alkaline earths. They have similar behaviors. Now the middle group in here, right? This group in here, they have some similarities, but they're sort of grouped together because they don't fit anywhere else. They're transition elements or transition metals. And that's obvious. They're transition from here to here. Now you might also see that these two groups and these six groups are brought together and called representative elements. That's largely because the trends that occur, physical and chemical trends from left to right, top to bottom, or across the periodic table are fairly well behaved, right? It's just when you get into the transition elements that the trends that we're going to talk about in the future, they sort of fall apart, or they roller coaster. But from here to here, representative elements, the trends that we talk about are relatively consistent. Oh, the rows are called periods. Has anybody had physics or physical science? You know about periodic motion? Right, there's linear motion and there's circular motion. Right, linear motion is if I could manage a straight line, I could run across the grass there. It'd be a linear motion. Or if I had a string with a weight on the end and went like that, that's circular motion. Periodic motion is a movement of something in a direction where it comes back and it ends up in the same place it was before. It's moving, yeah, but it goes back. Think of a pendulum on a clock. Like that's periodic motion. Use that in these terms. The characteristics, you go from left to right, you get characteristics here from left to right that are changing. And then you go to the metal, and then you go the next, add another proton, you get out here. Well, it turns out that that one looks like this group. So instead of just making another column out here, we return to where we were. we complete the period. And we form a new row, which is a new period. Okay. So there's, oh, I left out the two groups down here on the bottom. The lanthanides and the actinides. The lanthanides they go right in here. And the actinides go right in here. Because they fit where lanthanum transitions to hafnium, right? 57 to 72. Then you fit this whole row right in there. You fit this whole row right in there. They're pulled out for two reasons. One is so your periodic table won't be a mile wide. And the other is because, we're going to learn this later, the way these atoms are built, these guys, we're adding electrons into energy shells, the same energy shells here. They're different, but they're similar. That doesn't make a whole lot of sense right now, but it will. So it's the way we build the atoms. The periodic table is organized so that you can determine the electronic structure of your atom simply by reading the table. We're going to get to that eventually. And that's one of the reasons that we bring those out, because the orbitals that are being filled by electrons are, I'll just say it, they're f orbitals here. These orbitals are being filled with d orbitals. These are s orbitals, and these are p orbitals being formed. So it gives you a taste of what's coming. All right. Now, one other thing that's essential for you to know is when we start to name compounds, you have to know which elements have fixed charges and which elements, when they form ions, which have fixed charges and which have variable charges. The alkaline metals, the first group, they're always +1. Alkaline earths, the next one to the left, they're always +2. Halogens are always -1. Noble gases are zeros. They're -1. Now, when you're in ionic compounds, the oxygen group is always -2. Nitrogen group is always -3. Boron, aluminum, gallium, and indium, I think, are always +3. So those are fixed charges. The rest of them are variable. All but, let's see, copper, silver, and cadmium are always +1. +1, +1. And, oh wait, copper, silver, and +1. No, it's the other way. Silver, cadmium, same. +1, +2, +2. Those are fixed charges. And all you have to do is look at the periodic table like this. Oh, it's at the back of your review document. And it'll show you. Yeah, zinc is +2, cadmium +2, and silver is +1. Those are fixed. Okay, naming compounds. I'm going to run out of time. Compounds can be named in one of three different ways. And this is the starting point for naming compounds, right? It can get complex, but this is the beginning. Binary compounds, that is two different elements together, or two different groups, actually. Type 1 compounds. These are formed from metal and non-metal. Okay. The metal has a fixed charge. So type 1 compounds are always formed from metals of group 1, group 2, alkaline metals, alkaline earths, or here. Or these three. That's type 1. Type 2 are also metal, nonmetal, but the metal has a variable charge. It could be, and it's not variable once the compound is formed, it's that it has the potential to have more than one charge in different compounds. So those are typically the transition metals and some of these guys. And then type 3, these are nonmetal, nonmetal. Okay. So if the metal is a fixed charge, you don't have to say what the charge is because you know what it is. Say you have, well, like sodium chloride, table salt. We would just say the first one is always the cation, sodium. And then the second one, we change it to the ending of IDE, chloride. And that's all you have to say. There are two rules that are overriding naming compounds, nomenclature. One is the name must be unambiguous. That is, when you name sodium chloride, it can't be anything but NaCl. Right? And the other is unambiguous and I had it on tip of my brain here for a second. I want to say non-repetitive, but that's not the right word. Okay, it'll come to me. Boom. Almost had it. Non-redundant. You don't want any more information in there than you need. Okay. So if we were to say, how about this one? Silver chloride. That would be +1 charge, -1 charge. That's it. Or if you have this, how would you name it? Well, the temptation is if it's a transition metal, you want to say what the charge is, but it can only be one charge, right? So you wouldn't say this, right? The charge. That's reserved for type 2s. So type 2, say we had iron. Let's do it this way. We have iron together with oxygen. And iron happens to be, in this case, a 3+ charge. It could be a 2+ or it could be a 3+. But in this compound, I want it to be a 3+ charge. And that means oxygen's a 2- charge because of where it is. So how would we balance that compound and write it correctly? You need the same number of positive charges as negative charge. Right? So something like this, where you have an odd and even, just cross multiply. Bring that 2 over here and that 3 over there. And 3 times 2- is 6-, and 2 times 3+ is 6+. Balanced your charge. That's how you do ionic compounds. You balance the charge for neutrality. How would we name this? Well, we have to say what the charge is because we know it's variable for iron. So we say iron, oops, not Arabic, Roman numeral. Iron 3 oxide. That's how you name a type 2 compound. You say what the charge is in the name. If you didn't do that, then you don't know what it is. Right? If it's just iron oxide, it could be iron 2+ or iron 3+. Okay. Non-metal, nonmetal. You can't balance the charge with non-metal nonmetals because they're covalent compounds. These are all ionic compounds. These are covalent. So that means nobody's got a charge. So what do we do with these? You say how many of each atom is in each molecule. All right. So if we had, let me make one up. Say, how about this one? We know that there are 2 phosphorus and let's not do that. Let's do chlorine. Like that. Okay. How would we name that? We use the Greek prefixes. Let's see. We got examples there, examples there. We'll come back to the polyatomics in a minute. Here we go. The Greek prefixes: mono, di, tri, tetra, penta, hexa, hepta for 7, octa, nona, and deca for 10. Those are the only ones I want you to memorize. There's a whole lot more, but that's enough. So here we have di phosphorus. And we treat the chlorine, we borrow from type 1s and type 2s. Instead of saying chlorine, we're going to say chloride. Now we say penta. Chloride. So diphosphorus pentachloride would be that molecule. We have to say how many there are because they're not charged. We can't balance charges. Now, if we have something like this one, like that, if there's only one of the first one, say in the metal position, it's not a metal, but it's in the metal position, we don't say mono. We just say nitrogen dioxide. Okay. Or NO would be nitrogen monoxide, or everybody's favorite CO, carbon monoxide. Okay. Let's go back to polyatomic ions. I gave you a separate handout. It's also in the review document. Polyatomic ions. The way this table is set up is so that and the left-hand side is the same as the right-hand side. Only the left-hand side is sorted by the name of the polyatomic ion, and the right-hand side is sorted by the formula of the polyatomic ion. So you don't have, 40 or 50 different polyatomics. You only have half that many. Just the left is sorted one way and the right sorted another way, if you're looking them up. And the names for the polyatomic ions are fixed. So when you put them in the compound, you don't change the name. Okay, so if we have, how about this one? That. This is a polyatomic ion, acetate, and this is sodium. What type of compound is this going to be? Type 1, 2, or 3? Well, you got a metal, so it's either 1 or 2. And the metal is a fixed charge, so it has to be a 1. So we have sodium, acetate. If you look up there at the top, acetate is C2H3O2 with a minus charge, and that's a +1 charge, so the charge is balanced. Okay? So the polyatomic, what you'll notice is all but one of those polyatomics is negative charge. There's only one that's a positive charge in this list. That's ammonium. So if we have ammonium acetate, we would have NH4, which is a +1 charge, and acetate, C2H3O2, which is a -1 charge. So one of each. Okay. The other rule you have to be careful about is these behave as a single unit, right? That charge doesn't belong to the oxygen or the hydrogen or the carbon. It belongs to the whole group. So if you need more than one of these negatives, you've got to put a parentheses around them. Do like that. Say, in this case, if it were magnesium, then you need two of the negatives. You have to use parentheses with polyatomics. You can't change the subscript. They're chiseled in stone. It'll take practice. I won't deny it. Okay, I'm over time. Binary compounds. Now, I think the last naming convention is for acids. Well, the next to the last is acids. So, let's define an acid in chemical terms. For our purposes, binary chemicals, acids start with hydrogen. That's the first element in their name. So if we did this, then if we named it by our convention, this would be a type 1 compound. This would be hydrogen chloride, right? And that's what it is if it's a gas, hydrogen chloride gas. But if you bubble it through water, if you dissolve it in water, then it becomes aqueous, AQ. It becomes hydrochloric acid. Now notice what we've done there. You have to have the at least one of these. Sometimes you have two or three in the first elements in the compound. And sometimes there are hydrogens in the rest of the molecule too. But those hydrogens don't contribute to the acidity. They are bound. But these can be separated from the molecule, and that's what gives it its acid characteristic. So with, say, acetic acid, right? You're making a salad with vinegar and oil, you're using acetic acid and vinegar. There you go. That's the hydrogen that makes it sour. These hydrogens are stuck. They don't move. Okay. So this would be hydrogen acetate. That's a polyatomic ion. But if you put it in water, then the 8 becomes ic. And this is acetic acid. Now notice the difference here. I started this one with hydro, but I didn't start that one with hydro. That's the naming convention. If the molecule has oxygen in it, you don't start with hydro. It's only when the oxygen is absent that you start with hydro. And then you say chloride becomes ic, or ATE becomes ic. These naming conventions, what we're trying to do is standardize the naming convention based upon what we were grandfathered by alchemists, because they'd already named these things, and we needed to standardize them so that we could proceed to other compounds logically. All right. So hydrochloric acid is this one. H2S, hydrosulfuric acid. Sulfide becomes ic, and we say sulfuric just because it sounds better rather than sulfic. Cyanide is a polyatomic ion, Cn minus, cyanide ion. So it's hydrocyanic acid. If they're dissolved in water, okay, that makes them acids. If it's HCN gas, right, which would be deadly, is hydrogen cyanide. Okay, here's some polyatomics. Nitrate becomes ic, HNO3, nitric acid, and just assume that these are dissolved in water. SO4, sulfate becomes ic, sulfuric acid, and we did acetic acid already. Actually, vinegar is 5% by weight. Acetic acid in water. Okay, NO2 is not nitrate, it's nitrite, and ites become us. So whereas HNO3 is nitric acid, HNO2 is another polyatomic ion with the same charge, -1, This is nitrous acid. Okay. And SO3 is sulfite rather than sulfate. SO4 is sulfate. SO3, 2- is sulfite. So that's sulfurous acid. Okay. Let's see. And there's a chart, flow chart for acids. All right. I will give you one example. If you're planning on heading into chemistry, or if you're just interested, these polyatomic ions, some of them have a pattern to them. And this one, right, that is the chlorate polyatomic ion. If we take away one oxygen, we get chlorite. And if we take away another oxygen, we get hypochlorite. Right, hypo underneath, like hypodermic, under the skin, underneath chloride. And if we add one more oxygen, we get perchlorate. Okay, so you got a sequence of 4 here just by starting from there and working your way down and up. And you can do this with any of the halogens. Put bromine in there, it's perbromate, bromate, bromide, hypobromite. You can use iodine, that's periodate, so forth. So you can get 12 just like that, 12 of these names, just like that. Now, if we make acids out of them, notice that protons are +1 charge. So you only need 1 proton for each of these. If we add a proton for each one, and they've all got oxygen, so we don't start it with hydro, then this would be perchloric acid. This would be chloric acid. This would be chlorous acid. And this would be hypochlorous acid. Okay. Let's see. I know you've seen this one before. Well, you don't read labels, do you? Okay. Read the labels on a bottle of bleach. There you go. Sodium hypochlorite is bleach. Now, there's various compositions. Some of them used to be 5% was all you could get. Now you can get 6.5% regularly. Okay. So I think that's close. Which of the following compounds is named incorrectly? In this case, you see, is it a type 1, type 2, or type 3? And then you see if that matches the name. Potassium is a type, would make it a type 1. Potassium nitrate, that's correct. Titanium is in the transition metals, and it's not one of these. So we have to figure its charge. Oxide is 2-, so 2 times 2- is 4- total, right? So that one titanium has to be 4+. And it's not named correctly. that needs to be a 4 Roman numeral, not a 2. OH, hydroxide, that's a -1 charge on a polyatomic ion, OH. So it's -1 times 4, and that means 10, SN has to be +4, and it is in the name, so we're good. PBr5, those are both nonmetals. So phosphorus pentabromide is correct. Chromate is a polyatomic ion with a 2- charge, and calcium has a fixed 2+ charge, so 1 of each is all you need. That's good. Calcium chromate is correct. The only one that's wrong is that titanium compound. Okay. Oh, last one, waters of hydration. Reason I stuck this one on here is because we have a lab. I think it's the 3rd lab where we're actually going to determine the waters of hydration for a compound. What do we mean by waters of hydration? When metal compounds are either precipitated from or left after water is removed from them, dissolved in water, they're left behind. Typically what happens is if you heat them to dry them, say at 105 degrees Celsius, drive off the water, very often there's some water left behind in that crystal structure. Those are waters of hydration. They exist as water molecules in the crystal matrix. Okay. So when that's the case, and our example here is zinc sulfate. Now you can get anhydrous zinc sulfate, that's possible. They just heat it to about 150 degrees Celsius for a couple hours. You'll drive off all those waters of hydration. But it typically, if you only dry it at 105 degrees, it typically has 7 waters in molar ratio of 7 water molecules for every 1 zinc sulfate unit. That's the ratio. The one we're going to do is copper sulfate, and it has 5. Now, just because you know that doesn't mean you don't have to do the experiment. You can do the experiment and prove it, okay? But the way we name them, we name these just like we did before, right? Copper could be copper 1 or copper 2. In this case, it's copper 2. So we would say copper 2+ charge, sulfate, and then we say hydrate, and how many of them are it? So in this case, there'd be penta. Pentahydrate. That's how you name a compound waters of hydration. Okay, I think that's the last slide. Yep.